This program is brought to you by Stanford University.
Thank you very much. Is the microphone on? I can't hear from here. There's no feedback. Okay. Thank you, Robin, for a very kind introduction, and thank you all for coming to listen to my confessions. It's kind of intimidating to be confessing in public in front of so many people. I think I'll feel a lot better at the end of this confession. It helps, to confess sometimes. Anyway, my confessions really start with the day that I started lecturing at Harvard, which is much longer than I want to admit, much longer ago than I want to admit. I came to the US actually as a postdoc. I was never going to become a professor. I was going to work in industry. I had a job actually lined up at Philips in Eindhoven, and my dad said to me, why don't you take a one-year postdoc in the US? So I called Philips and I asked them, is it okay if I defer my appointment for 1 year? And they said, sure, learn more about optics. So I went for 1 year. It's been a very long year. Anyway, in 1984, 2 years after coming to Harvard as a postdoc, I joined the faculty as an assistant professor, and I started teaching. And my first confession is actually that the biggest mistakes I perhaps made, the biggest mistake I perhaps made was made right then. I never asked myself what the goals would be, what I would do in the classroom. I knew I'd been assigned a big pre-med course, which I'd happily accepted a teaching assignment. I didn't know that nobody else wanted to teach that course. That's how naive I was. But I never asked myself, how am I going to teach the course? I just did what had been done to me. Now, I think that's a pretty natural thing. We all do that. We project our own experience onto the people we meet. We think that other people are going to be the same and going to have the same experiences as we have. And I think there were two mistakes there. One is most of the people we teach are not like us. They're not going to become professors. In fact, in a completely steady state situation, you're entitled to exactly one successor, right? Otherwise, within a couple of years, the entire planet is going to be physics professors. So among the many thousands of students that we teach, there's perhaps one who can become a professor like us. So most of the students are going to be very, very different. The other thing is that in hindsight, I am not so sure that what I know now and what I've accomplished is all a result of the teaching that I experienced as an undergraduate. I think it might be even perhaps safe to say, and I'll work on trying to convince you of that I am what I am in spite of my education, not so much because of it, and that most of the learning happened afterwards. In fact, it's still going on. It started after college. It didn't begin in college and end at the end. Anyway, so I taught the large pre-med class, and I went by, and I did that for a couple of years, 1 or 2, and by the end of the second year, I was convinced that I was actually a very good lecturer, because by the standard assessment, I was succeeding. What is a standard assessment? Well, I can think of two things that come back to mind to reinforce that feeling of being a good lecturer. One was the end of semester questionnaire. Most faculty, when they teach the pre-med course at Harvard, come close to committing suicide at the end of the term when they get the results of their questionnaire. But not so for me. I got 4.2, 4.5 on a 5-point scale. So clearly the students were enjoying or liking what I was doing. The second thing is that I could give these pre-meds, who were not going to be physicists, quite complicated problems. Most pre-med courses are algebra-based. At Harvard, we teach a calculus-based course. I think you do the same here at Stanford, I'm not sure. But it's a calculus-based physics course. And I could give these students pretty complicated problems. A stick is lying on a frictionless surface. It's hit by a puck, which sticks at some position on the stick. The two start to rotate about their common center of mass. Find an expression for the angular position and translational position as a function of time. I'm not sure I could do that under the pressure of an exam. But my students, by and large, did well. So in short, they did well on the examinations I gave them. They gave me high ranking. Obviously, I was doing the right thing in my class. Now, there were some signs that deep down something was amiss. You know, in spite of giving me high rating, each time that I taught, a couple of students would write down in that free response section at the end of the questionnaire, "Physics is boring," or "Physics sucks." I didn't know what to make of those remarks, so I just systematically ignored them. You know, and then when I'd go to a party and people ask me what I do for a living, and I tell them I'm a physicist, and people would get this scared look on their face. Physics? I had such a tough time with physics in high school or in college. It always creates a sense of embarrassment. I never know how to react, and I wonder why it is that physics causes these reactions. I think I know now. Or my dentist, you know, recently told me, and I couldn't even talk back to him because I had the thing in my mouth, right? He said, "Oh, you're a physicist. I got an A for physics in college, but I really never understood anything." Anyway, I decided, since I didn't know what to make of those remarks, I decided to simply ignore them and go on, because I knew I was a good teacher. So that went on for a couple of years. And then in 1990, about 7 years after starting to teach at Harvard, I came across a series of articles in the American Journal of Physics that described a conceptual survey of Newton's laws called the Force Concept Inventory. Could I see a show of hands of those of you who are familiar with the Force Concept Inventory? A few, but it's a minority. So I better explain to you what the Force Concept Inventory. So a typical physics course will start by describing motion. There'll be a little bit of physics in this talk because I'm a physicist and I have to give you this talk, these confessions from my perspective. But this talk is not about physics. I'll use a few examples of physics, and I think you'll be able to follow most of them. But if you're a chemist, each time you hear me say the word physics, just mentally substitute chemistry in there, because I think that most of what I say applies to chemistry, biology, in fact, to most disciplines. Anyway, so the Force Concept Inventory deals with Newton's laws, which are typically treated in the second or third week of an introductory course sequence. You start describing motion, then you talk about Newton's laws, and then everything else builds on these concepts developed in Newton's laws. So it's the basic building block of most of the introductory physics course. Now, the Force Concept Inventory has about 30 questions, which are multiple choice questions that deal with the understanding, the conceptual understanding of Newton's laws. Let me give you what turns out to be one of the hardest questions on this test. A heavy truck and a light car collide head-on. The force of the heavy truck on the light car is A, larger than that of the light car on the heavy truck. B, they're equal to one another. C, the light car exerts a larger force on the heavy truck than the other way around. D, they're not exerting any force on each other. They're just in each other's way. Now, you're laughing about that. I don't think any physicist in his right mind could ever come up with such an answer. And that actually is a weakness of multiple choice tests. You know, if you know your stuff and you design a multiple choice test, it's very easy to come up with the right answer, but it's very hard to come up with plausible wrong answer. So the Force Concept Inventory, which was developed by David Hessenes at Arizona State University, started with questions that were free response. And then he tabulated the most frequent incorrect responses to address misconceptions held by students. And this, which I think no physicist could ever come up with, was one of the frequent responses. And the fifth one is I keep forgetting what it is. It's, again, one of these things that my mind cannot grasp. Anyway, you ask students in an introductory physics class, what's Newton's third law? Action is reaction. The force of A on B is equal to the force on B on A in any interaction. They can recite that law. You ask this question, and 60% is convinced that the heavy truck exerts a larger force on the small car than the other way around. So what Hessenes did was very interesting. He used this as a pre-test at the beginning, on the first day of class, and then again as a post-test at the end of the semester to see what the gain was and how many more students got that question and 29 similar questions correct. And because this test doesn't have any physics jargon, I mean, we all know what force is or have a concept of force in our mind even before taking a physics course. So, you know, you can stop anybody in the street and ask this question, and he or she will have an answer. Not necessarily the right one, but will have an answer. And then you do it again at the end. And the first paper that I wrote, somebody actually sent me those articles and I read them, said that there was very little gain in introductory physics courses taught actually in a number of large schools in Arizona, New Mexico, and California. And I shook my head because, you know, I was educated in Europe and we did this in high school, and by the time we started our college education, we did classical mechanics. You know, I mean, it had nothing to do, this test had nothing to do with what I did in my class. This was a calculus-based class. And, but then in the second article, because he had so many data points, he had about 5,000 data points, he was able to analyze the effect of the teaching approach on the pre to post test. He had, first of all, teachers who taught large classes, or students of teachers who taught large classes. That was one group. Then another group where the instructors didn't like large classes and broke down their classes in small groups of 20. Small group instruction. Then teachers who like to do a lot of hands-on demonstration, and a fourth group. So for each of these groups, I forgot what the fourth group was. For each of these groups, he did pre and post testing, computed the gain, compared the gain. And you know what? Oh yes, the fourth group was of the teachers that had gotten the lowest possible ratings on the end of semester evaluation. Right. And the first one, the large classes, were award-winning teachers. I forgot to say that. Anyway, so for each of these four groups, he took the gain, compared them, and you know what? No difference. It doesn't make any difference what we do in front of these students. It doesn't make a difference whether we win teaching awards or whether we score at the bottom of the scale on the teaching evaluations. Well, you can imagine my reaction. I probably very similar to your reaction right now. I shook my head in disbelief and I said, not my students, not Harvard students. But you know, I've been trained as a scientist, so you learn not to make just assertions, but to get data and disprove or confirm a theory. So I felt challenged, and I thought, I'm going to show that my class things are really, really different. So I set out to test my students. Now, we were already in the middle of the semester, and we were dealing with rotational dynamics. Students had to calculate triple integrals to get the moment of inertia of complicated shaped objects. I mean, this was already, you know, this was covered in the second, Newton's laws was covered in the second week of class. It was so trivial compared to rotational dynamics. But I was so eager to get data, I decided I was going to trick my class into taking this FCI seriously. So I announced in class, I said, look, I'm going to give you an extra quiz. I didn't want to call it a test. Actually, I called it a questionnaire. And all the euphemism we invent, right, for our students. Anyway, so I said, look, don't worry about it. The score for that questionnaire is not going to affect your final grade in any way. It's for me to be able to assess the effectiveness of my own instruction. And, but I realized that I also had to give the students some incentive to take this. So I told them, if you take this questionnaire seriously, it will help you pinpoint any difficulties you will have, and it will help with the upcoming midterm. We had a midterm that was coming up. And then as soon as I said that, I thought, I've told them a lie. You know, that once they see this questionnaire, they'll be offended by the simplicity of the questions. But oh boy, were my worries quickly dispelled. Hardly had the first group of students taken their seats in the computer classroom where we administered this test, this was back in 1991, or one student raised her hand and she said to me, Professor Mazur, how should I answer these questions? According to what you taught me, or according to the way I usually think about these things? How do you answer such a question? Well, by the time the test had been completed, I had been dragged out of my ivory tower, and life has not been the same. Thanks. Well, with that long introduction, let me get started here. The message that I want to get across, and it may sound completely trivial at this point, is that we should really shift the focus from teaching to helping students learn. And you know, it may sound very trivial, but I'll add some meat to that statement. And I'd like to do that in three parts. We'll talk a little bit about education. What is education? What do we hope to accomplish? And then I'll talk about what I've done in my classroom in response to this disconcerting discovery that I just told you about. And scientist that I am, I want to show you some results that we've obtained. So that's the program for today. So let's start with education. Step into any classroom anywhere on this planet, and you're likely to see this scene in front of you. In fact, this is my classroom a while back. That's me about, probably 18 years ago in the Science Center, which is a building dedicated to science, teaching undergraduate courses. Amphitheater seating, like almost all of our classroom. Now, I actually make a habit of, from time to time, stepping into classrooms of random courses. They're psychology courses, bio courses, and just observing. It's very interesting. I urge you, if you teach, to sometimes do that. Just step in the back of a random class and observe. You get a very different perspective from the one in front of the class. From looking at the back, you become more aware of what students actually do during your class. Very illuminating. And ask yourself, how many students are actually paying attention or asking questions or taking in what's happening? But the other thing is just to ask yourself, what is this activity? What is going on in this classroom? How would you classify this? What is this? What is going on? And don't use words like teaching or learning.
Lecture.
Lecture, yes. Lecture, incidentally, comes from the Latin verb for to read, which is what indeed happens in many classrooms. I'll come back to that in just a second. Lecture, yes, but what is this process of lecturing? What does it do? What is it? It's focusing on what?
The presenter presents and the students write it down.
The presenter presents and the students write it down. That's right. It's basically a transfer of information. Right? It's a transfer of information. We live in an information age. There are many ways to get information now. Books, computers, TVs, you name it. Until probably the Industrial Revolution, this was the only way to transfer information. Right? And education has to start with information. In fact, the students had rubbed this in my face. But this was again one of the things, next part of my confession, that I had ignored. The first year that I taught, I went to my colleague who had taught the course before. I said, what book did you use? And he said, oh, we use Haldane Resnick. I went to the bookstore, ordered Haldane Resnick. And then I thought, what am I going to do in class? So I went back to him and I said, what do you do in class then? And he said, well, there's a number of other books, and here are a couple, and you can use those to prepare your lecture notes. So when I looked and I found one that was actually conveniently out of print, Widener and Sells, they had a slightly different approach. So I thought, that's great. I'm going to use that book to prepare my lecture notes to lecture from. But because the Widener and Sells has a slightly different approach, I thought it would be good for the students to have copies of my lecture notes. So for each class, I prepared about 10, 11 pages of lecture notes that I lectured from. I projected some, wrote some on the board. And at the end of each class period, I gave copies. I handed out copies of these lecture notes at the end. Why? Because I didn't want students to come in, grab the information, and then walk away, which in a sense is already admitting that there's a problem, right? Because why not? Anyway, at the end, 4 weeks into the course, a number of students come to me and they say, Professor Mazur, couldn't we get a copy of the notes at the beginning of this class period? This way we don't have to write down that much. And I had indeed noticed that every time my pen went A on the overhead projector on the blackboard, 150 pens went A in the notebooks of the students. I once heard, and this comes back to a remark that one of you here made, I once heard somebody describe the lecture process as a method whereby the lecture notes of the instructor get transferred to the notebooks of the students without passing through the brains of either. Well, that's precisely what was happening in my class. I was taking this book, this perfectly well-written book, turning it into lecture notes. In class, I was putting it on the blackboard, and on the overhead projector, they were copying into their notes. Anyway, so I thought, maybe I should give it out. So I gave out the notes. I started giving them out at the beginning of each class period. And much to my relief, students wouldn't just come in, grab the notes, and walk away. They grabbed the notes, sat down, and still copied everything because they had no time to see what was in the notes. The next year that I was teaching that same course, I said to myself, you know, rather than handing out these notes piecemeal, one time at a time, why don't I take them over the summer all to Kinko's, have the whole thing duplicated, and at the first day of class, I give them the whole pack of notes at once. So the students got the textbook, and they got my lecture notes, and went on. What happened was that at the end of the semester, about half a dozen students wrote, Professor Mazur is lecturing straight from his lecture notes. I was livid. What was I supposed to do? Prepare another set of lecture notes to lecture from that was different from the first one? I was furious. Suppose I'd been teaching Shakespeare rather than physics. I mean, I think that's maybe interesting to pause about for just a second. I don't think I would have done the same thing. I wouldn't have said, well, next Thursday we're treating A Midsummer Night's Dream. No, I would have not said anything. I would just have had the people come to class and say, today we're discussing Midsummer Night's Dream, and then start reading the play to them. No. I would have told students, next Thursday we're going to discuss Midsummer Night's Dream. If you haven't read the play, read it before coming to class. And then in class, we would have discussed some passages, put the play into a historical context, and so on. The reading of the play, the transfer of information, happens outside the class. The class is meant to deepen the understanding for the material, but that was not really what was happening in my class. So I think, you know, whenever you see this setting, the emphasis with students sitting passively, all focused on the teacher, what is happening is that there is a focus on the transfer of information from one generation to another. Is that what education is? I would say if you stop to think about it, we all very quickly will agree, no. Because you have to take that information and make sense of it, assimilate it, connect it to things you already know from experience, or resolve any misconceptions you might have. You have to assimilate the information that is transferred to you. And I think that assimilation is actually the hardest part, right? Between, if you think of education as a two-step process, one is getting information, two, assimilating that information. That second step is much harder than the first one, especially now that information is poured at us out of, you know, all corners of the world, everywhere, whatever we do. So I think that, and I think also, you know, in a traditional approach to teaching, that assimilation is supposed to happen on its own. In fact, you know, if I couldn't understand something in class, I stood over it after class and resolved it. But again, my experience is not the same as that of most of our students who do not go on to our career that is very similar to ours. And, you know, I think that the first time I gave the FCI, the Forced Concept Inventory, it became clear that education is not just a transfer of information. So here's a histogram that shows the number of students on the vertical scale versus the score on the horizontal scale. In 1990, the FCI had 29 questions. When I took the FCI, I got 28 out of 29. I must have misread a question or something. I actually made a genuine mistake. But anyway, you expect anybody who really knows his physics well, including most of your students at the end of an introductory course, to be in these last three bins. Now, this was the pretest. And as you can see, there are students who score only marginally better than just randomly answering questions on the computer. Anybody who scores below 23 has really no consistent model of Newton's laws, is still partly an Aristotelian thinker. And as you can see, my incoming class, about 2/3 or so were still Aristotelian thinkers. Now, this was at the beginning. I was teaching a traditional course, lecture course, in 1990. What about the end of the semester? That's the data at the end of the semester. Same students taking the exact same test again a second time after perfectly being, you know, able to solve triple integrals and other things and rotational momenta and you name it. Okay? But the FCI, this is how they score, and you can still see that about half the class has no clue of Newtonian mechanics, which is treated in week 2 and on which everything else is built. Well, here's the gain. We've moved some students up, but nowhere near as much as we want. Let me plot it differently. I'm going to put the initial score on the horizontal scale. I'm going to put the gain, the initial average score for the class, and I'm going to put the gain on the vertical. So the data point is there. The initial score was 70%, and the gain was a whopping 8%. Now, where do you want your students to lie? You want to lie on this diagonal line, right? If they score 40 initially, they can gain 60. If they're 70 initially, they could gain 30. And as you see, we've only gone a tiny little bit towards that slope. How does this compare to other institutions? That's a Harvard point. Here are many others collected by Dick Hague. Here are community colleges, Ivy League school, large state schools. And you can see that the community college starts out much lower, but has a much bigger gain. Of course, they have further to go, but they have a bigger gain than the Harvard gain. A bigger absolute gain. In terms of fractional gain, they're actually all the same. We can take all of these data together, and we see that they only get to about a quarter of what they could be getting. Whether it's a community college or an Ivy League school, the traditional method only gets you a quarter of the way to where you would like to get. Now, so the point I really want to make is, and I already made it, but let me reinforce it, it's not just the transfer of information, it's the assimilation. And the lecture does not provide the opportunity for people to assimilate information, only to write it down and to try to memorize it. Now, the other problem that I discovered was that the assessment that we use in our classes actually gives a very misleading picture and reinforces everything that's bad that we do in our classroom. Or at least that was true in my own class. I'll let you draw your conclusions about your class. When I gave this FCI, I thought to myself, and I thought, how can this be? How can these students do so well on much more complicated material and so poorly on these simple questions? I mean, maybe that the FCI, that's just semantics, right? After all, well, the first thing, okay, let me step back for a moment before I put words into your mouths, because I want to have some feedback from you. The first thing was that I thought, well, maybe I'm not that good a teacher after all. But I didn't think that very long. I knew that couldn't be true. So my next attempt at trying to explain why the FCI had not given me the result I wanted was, dumb students. But it's hard to maintain that at a place like mine or like yours. So I thought about it a little bit more, and I came up with the perfect excuse. Very good. I usually have to pull at the audience to get that out. Bad test, exactly. And I said, look, if you have never had physics and you're asked a question in a collision between a truck and a car, where would you rather sit? You don't need to take physics to know that you're much better off in the truck than in the car. So I thought maybe that people are confusing, damage with force. Rather than connecting it to acceleration and mass. And I thought maybe this test is more a test about semantics than about really understanding the underlying concepts. After all, if I asked the students what is Newton's third law, they would all recite action is reaction. And if we did a problem, they would mostly correctly identify force pairs that were equal in magnitude to one another. What I didn't realize was if you ask a professional physicist to do the FCI, they all end up on really high score, including most graduate students. So if you understand it, there's no trouble identifying the right responses. But anyway, I decided to do some more probing of my own because I couldn't really reconcile this information. I decided to actually, on midterm examinations, put two types of problems on the same day. So same students, same topic, but two types of problem. One, a traditional problem, like this one. We have two loops, two batteries, and three resistors. This is the only little bit of physics that I'll have in my talk. And the students were asked to calculate the current in the 2-ohm resistor there and the potential difference between the points P and Q. Now, again, the physics doesn't matter here. But to solve this is not a really hard problem. But if I were to give you all a piece of paper and we try to work out this problem, and then after 10 minutes compare our answers, many of us would have made a mistake. It's about 2/3 of a page of equations, and there's ample opportunity to make mistakes. Forget a minus sign or a factor of 2, this, or make a wrong substitution, you name it. So this was problem number 5 on a midterm examination. Problem number 1 was this one. It was a same subject, and it was 3 light bulbs that are connected in series to a battery, and there's a switch that shorts out this last light bulb. Now, don't try this at home, but if you short out a light bulb, all of the current goes through the short and nothing goes through the light bulb, because this is infinitely less resistance to current than that. Again, don't try this at home, it's dangerous. So the students were asked, when this switch S is closed, these 3 identical light bulbs, what happens to the intensities of light bulbs A and B? What happens to the intensity of light bulb C? What happens to the current through the battery, to the potential difference across the 3 light bulbs, and to the total power dissipated? If you know DC circuits, it takes you 30 seconds to answer. Oh, by the way, the only thing the students were asked to say was it increases, decreases, or stay the same. I told them, it's not on the slide here, but I told them that they didn't need to put anything else down but increase, decrease. So no justification, no calculations, nothing. That was actually a mistake. You should always ask for justification because it's the reasoning that matters more than just the answer. But I didn't ask any of that. Just increase, decrease, or stay the same. So if you understand DC circuits, it takes 30 seconds to answer that question, of which 25 are spent on part E. That's the only one that requires a little bit of thought. The other ones, you know, you just say it. Now, what I forgot to tell you was that the large courses at Harvard are taught by 2 faculty members. So in order to put this on the exam, I had to convince my colleague that this was a good exam question. So I showed him the draft of this question. He read it, and he looked at me, and he said, "Eric, you're out of your mind." I said, he had not been part of the fall term. He didn't know anything about the FCI. So I said, "I don't think so." And I explained to him about the FCI and mechanics. And he looked at me, and he said, "But Eric, we only have 5 problems on this midterm. We cannot give away 20%. So that's why we made it problem number 1, the warm-up problem. Well, it turns out the students overheated on this problem. Professor Mazur, this problem number 1 was the hardest problem in the exam, said one student. Or another student who said, "I didn't know how to get started on this problem." I mean, what do you mean getting started? If you're started, you're done, right? Well, I decided that I was going to grade problem number 1, and it was a little bit selfish because, you know, I thought I could do that in just an hour and a half for 200 exams, because only I had to see is increase, decrease, stays the same. It took me a whole weekend. Some students had freaked out and written 6 pages in their blue books. They had written just absolutely everything they knew about DC circuits in hopes of covering the right answer. Some were talking about RC times. This is an insider joke here. I mean, for those of you who understand, I mean, they talked about everything that had been covered in the subject of DC circuits. And I had to hunt in all this mess for increase or decrease. Well, and you know, by the time I'd finished grading, it was clear that we had a problem. Here's the histogram of scores on the conventional problem, so number of students versus score out of 10. And to the right is on the conceptual problem. And you can see that the average for the conventional problem was 7 out of 10. The average on the conceptual was 5 out of 10. Do you see that huge peak at 2 there, right? Because they had written down so much, I was actually able to reconstruct their thinking. And it turned out that 50% of my students had made the following basic assumption. They said, when the switch S is closed, nothing happens to the current here because it doesn't know yet that the switch is closed. So it arrives at this junction that this does before. And then what does it do when the switch is closed? It splits in 2. One half goes straight, the other half takes the turn. So what does that do? Well, nothing changes to the current here. That's not true because if you connect 2 light bulbs to a battery, they draw a lot more current than when you put 3. It takes more resistance to go through 3. So that was wrong. So they lost 2 points on part A. What about part B? Well, half the current goes through. So what did they write down for C? It decreases. You know what? That's where they got their 2 points. I'm not joking. I told them that the only thing I would grade on was increase, decrease, or stay the same. So I had to be fair, and I did it. Doug?
I was going to wait till the end, but of course you and I know that the resistance versus current is very complicated.
In a real light bulb.
Right.
Yeah.
And I show that in my lectures. I don't know if you do.
I can tell you much more about this. We actually had a lab that had light bulbs and batteries, and half the class had that lab, which allowed me to separate the results, lab and not lab. Let's talk about that later. Okay. So that's that too. So actually the results are a lot worse than I show in that diagram, right? Because all those 2s really deserve 0s. You know, some of these, I have to go back here. These are pre-meds. You know, some of these are going to be surgeons who do bypass surgery later on. Anyway, same students, same day. Harvard students too. So naively, you would expect there to be some correlation between these scores and those scores, right? Students who do better on one type of problem should do better on the other. So I decided to plot for each student a data point that shows performance on both types of problem to see what that correlation is. Well, I'm afraid I have to disappoint you. Not much correlation. But if you look at this if first of all, if you're willing to relax your definition of a line somewhat, you find that about 52% does equally well or poorly on both types of problem. But now look around this band. Look here. Well, first of all, look here. 40% is right here, and that makes sense, right? About 7 out of 10 average here, and about 4 or 5 out of 10 average there. That's the bulk of my class. Here, there's hardly anyone. This is completely empty. This 9% is not a data point. Keep telling myself I should remove it to really, so that you see how wide it really is there. In other words, students who do well on the conceptual problem tend to do better on the conventional problem. Yet there are a number of students who get 100%. This, I think there were 6 or so students here, half a dozen, get 100% of the conventional. They're not even able to get those 2 points they could have gotten for free by assuming this 1/2 the current. So who are those 40% in my class? What are these students? How would you classify them? I beg your pardon?
Socially adjusted.
Well, maybe, but I think we have another term for them. What are they? Well, I don't.
They're following the algorithm.
How? They're following the algorithm. Plug and chug, right? I mean, they have been pre-programmed to sort of classify problems according to type and then to memorize the approach to solving that problem. So imagine you're pre-med. And you know, we can't blame these students for that. Open any physics textbook, and somewhere on page 20, there's this box that says problem-solving strategy. Read the problem, you know, make a drawing, choose your axis, right? So imagine you're a student, you're nervous, you know that your admission to medical school depends on your physics grade, and you see this box that says problem-solving strategy. You take out your yellow highlighter, and you highlight the section. It has already been highlighted by the publisher, but you highlight it anyway. And you memorize it. Because I think we can understand a lot of the problems in our introductory physics course by putting ourselves in the place of these 40 students. So you're afraid, you see this problem-solving box, you start to memorize it. Then comes your problem set. First problem. And you look at the recipe and you apply it, and it works. Why does it work? Because most of the problems we give our students are made to match the recipe. In fact, many problems lead the students by the hand. If they're too difficult, we break them down into little steps to slowly nudge the students from the question to the answer. And you're excited as a student because you think, yeah, maybe I can do it. I'll get into medical school. Then comes problem number 2, and you apply it again. And then comes problem number 3. And I have to admit, you know, I never was able to understand that somebody could think of physics as being boring. But if it is just applying recipes to problems, and you don't really understand the underlying reasons for the recipe, I have to admit, it is boring. So in this graph, you see that 40% of my class is predestined to think of physics as being very boring because they're doing things they don't understand. They're blindly applying recipes without understanding the underlying physics, right? They come to an exam, I give them an exam, and then comes problem number 5 or 4 on the homework. And you have the recipe, you have the problem, you try. It doesn't work because, as we all know, there are no simple recipes for all problems. In that case, the problem would no longer be a problem. It would be an exercise, or it would be, you know, just something to do. So if I were a student who was misled to think that there is a recipe-based approach to problem solving, but I discovered that the recipe only works 75% of the time, I'd get not only frustrated, but pretty mad too. What kind of professor is this who gives me a recipe that only works 75% of the time? So, you know, frustration, boredom, inability to answer simple questions, I think that's all the same phenomenon. And as you see, 40% of my class at Harvard falls in that category. Now you come to an exam. Professor Mazur is distributing the exam. It still was the printed side down. You're sharpening your pencil, quickly looking at your cheat sheet before, to cram in a few more equations in your head before the equation starts. And then the professor says, you may begin. And everybody takes their sheets of paper, and you hear 250 pages of paper being turned around, and you're the student. And as you turn it around, you see this diagram. What is the first thought that crosses your mind? You see the diagram. Kirchhoff's law. Wow, a sharp audience here today. Kirchhoff's laws, right. You've been pre-programmed. Diagram with wiggly lines means Kirchhoff's laws. For those of you who are not in physics or electrical engineering, Kirchhoff's laws are the laws that describe what happens to currents in circuits. So you've turned it around. We're talking about the first second, right, of the exam, and you see that drawing. You haven't read anything of the text. And you've made the identification, this is a Kirchhoff's law problem. Once you've made that identification, how much physics is left? 0. Maybe a little bit. You have to get the signs of the potential differences right. But next to nothing. It becomes an algebra problem, not a physics problem. Do my students understand Kirchhoff's laws? And the reason I'm showing this graph, no, because if they did, they would have absolutely no problem answering that question. Anyway, so, when I saw all these results, I understood it better, but I had the question, what should I do? And my first reaction was, maybe I should teach graduate classes. It's very different when you teach. I love teaching graduate classes too. Let's say, I've taught fluctuating hydrodynamics. I've taught optics classes. It's very different, right? The night before class, you take your binder home and you look through your notes and step 1, step 2, step 3, step 4, and then, oh my God, what justifies that step 4 again? And you know that you'll have a graduate student who will ask that question the next day, and you think about it, and you're about to go back to your office to look up in some books why that step is justified. And, oh, that's right. That's because I can make that assumption. Next day in class, you write down step 1, step 2, step 3, step 4, as if you always know. You look over your shoulder. Sure enough, there's a grad student who asks, and then you just answer the question. Because the question that comes up in our mind is very similar to those that come up in the graduate student's mind. Not so with introductory physics, because once you become really an expert on the material, it becomes hard to identify with a beginning learner. And we've mastered that material so long ago that we can no longer envision the problems that the beginning learner has. Anyway, so then I, by accident, discovered what the solution to the problem would be. After this FCI, I told you that I thought students would think of it as being too trivial, but it turned out that they actually found it very difficult. They didn't do that well. And they wanted me to have an extra lecture to go question by question through the entire FCI. Now, when we got to this question of the truck and the car, I made a drawing, 2 free body diagrams, explained it. I thought I'd give a really good explanation. I turned around, and I could see from the faces that they didn't get it at all, that those 2 forces had to be the same. So I asked if they had a question. But they were struggling so much with the material that they couldn't even verbalize a question. Right, so you can do 2 things then. You can just go on, or I decided I'll try it again, and this time I'll bring in the mass and the acceleration too, and we'll see that in spite of the forces being the same, the accelerations are going to be very different. I thought I'd really nailed it. And I looked around and I said, does anybody have a question? They were maybe even more confused than before. So, but I knew that about 50% had the right answer, so I said, turn to your neighbor and discuss it with your neighbor. I don't know what motivated me to do that, but I just did it. And what happened was something I'd never seen. They all started talking. I'd always lectured, and I would stop. Does anybody have a question? Anybody? You know, and if you wait long, the students look down because they don't want to look at you. If you wait long enough, it's always the same person in the front row reluctantly raised their hand. They don't want to interact with you. Here I said, talk to your neighbor, and it was total chaos. And what happened was that they were actually much more effectively convincing one another. Why? Because the students who understood it were still aware of the conceptual difficulties that the students who did not understand it. So it puts the better students in the role of teachers, reinforcing their knowledge, and it puts the weaker students in a position to learn from the better students. So I decided I'd do that in my classroom and give students more responsibility for gathering information so that I could be there to help them with the assimilation. So to think about education again as information assimilation, I moved the information stage out of the classroom. I give them my notes, but you better read them before coming to class because I'm not going to go over any of it. And then in class, I teach by asking what I call concept tests, which are basically conceptual questions on the information. So I'll project a question, give them a minute to think about it. Then they give their individual answers using clickers or laptops or cell phones. Then I tell them, talk to your neighbor and try to convince your neighbor of your answer. If they both agree, I tell them to try to find somebody who has a different answer, right? Because it doesn't make sense to talk to somebody who has the same answer. So the mandate is find somebody in the audience, get up if necessary, find somebody either near you or somewhere else in the classroom who has a different answer and try to figure out who is right. And then I have them answer again. So let's see a 60-second clip that is placed in a uniform magnetic field. I'm going to turn this down. So I read the question with them. I usually just project it, no high-tech here. That's the most reliable medium still. I read it with them so that we all agree on the question, and I tell them to think about it for a minute. And they think. I do not want them to talk to one another. I want individual commitment. So they answer it. We use the infrared clickers here. I see on my screen where the disagreement is at, and as you can see, the answer is split here. So turn to your neighbor and see if you can convince one another of the correct choice.
Right, it goes out of the page and the top goes in, so they cancel each other out. There is a torque. There is a torque. How do you know that? I said torque. What did you say? But how could it be a torque? Oh, so it was
That's the moment we all want to see, the aha. So, and let me show you, I will not show you results on individual questions. You'll have to believe me that there is consistent improvement on the individual answer. So that cycle repeats. If they do well on a question, I move on to another subject. If they don't do that well, I repeat another question on the same subject. Okay, quickly some results, and then we're done here. So I'm going to show you some results. Now, when a physicist says, I'm going to show you some typical result, it usually means I'm going to show you the best results I've ever obtained. I'm going to show you the results from the first year I implemented this. I was still groping in the dark. I did not know what the best thing to do was. Pre-test, most reliable and reproducible data I've ever had in my whole career. It's amazing. It must say something about the Harvard admissions office, I think. But it's the noise is different, but the average is within 1% from year to year. It's amazing. What about the post-test? Here it is. Even without seeing the pretest, that's already quite a decent distribution. You can see that now we have substantially helped the students in the lower half, and that some of the bins at the end are the highest. I made sure I was not using any question during the year that came close. In fact, in 1991, I went to the summer AAPT meeting. I gave a contributor talk. I don't know if any of you have been to American Association of Physics teacher meetings, but you get I think a 7-minute talk. So I spent about 5 minutes of my precious 7 minutes documenting that I had not taught to the test, because I didn't want people accuse me of saying, well, you've done this in class, therefore the test is better. And then at the end of my talk, somebody got up in the back and said, don't worry about teaching to the test. We've tried it. It doesn't work. So what about the gain? We've doubled the gain. From 8%, it went to 16% the first year. And in the years since, data points have moved up. The highest one was actually not obtained by me, but by colleagues of mine. It triples the original gain. What about other institutions? Also systematically higher. So the blue data points are the interactively taught courses. The scattering is a lot bigger because we're still learning what the right questions are to ask in class. But if you take all of the data together, you don't look at the best data, you see that simply implementing this doubles the gain on this instrument. What about problem solving? I mean, we're not just pre-meds, also engineers in my class. And if you design a bridge, which is conceptually correct, but it collapses because it only withstands a tenth of the weight it's supposed to withstand, you don't get any credit, right? And I knew my colleagues at Harvard would ask me this. So how do you test that? You test that by giving problems again. I hesitate to do that a little bit, but at Harvard, we only make 3 years' worth of exam public. And in the 8 years that I'd been teaching in 1992, or 1991, I had never, ever repeated a single question. So I thought, OK, I can't take an old exam, 1985, of which I had meticulously kept data, and repeat it. And I said to myself, even if the students do a little bit worse, I'm still happy because I know they understand the basics much better, as long as their problem-solving ability doesn't suffer too much. But you know what? They actually did better. The gain is not as big, but it's systematically, it's very systematic. It's very significant, I mean. It went from, I think, 62% to 64%. That gain was a real gain. It was not just in the noise. So what does this tell us? This tells us that better understanding leads to better problem solving. And in hindsight, that makes sense, of course, right? You understand the basics better, you become a better problem solving. But, and this is really my take-home message to you today, good problem solving is not necessarily an indication of understanding. I had been fooled for many years into believing that I was successfully educating my students. But all they were doing was really coping with the material, jumping through hoops, applying recipes without understanding the basics. So I want to thank you. I have a video clip about the students, but I'm not going to show that in the interest of time. I mean, I hope I've convinced you that some of the things I've done are worth trying. I'm never going to go back. My only regret is that I love lecturing, as you've undoubtedly noticed. So for that, I thank you for having given me the opportunity to lecture you.
Thank you so much, and especially those of you who are standing or sitting on the floor. You can see this in a chair. It'll be out on the CTL website within a week or so, and you can see it sitting down next time. But we have a moment, if you'd like, for a question or two. Stefan?
So from what you said, what do you actually do in class? You just ask questions, or
Well, initially what I...
and ask them to talk to each other. That's all you do?
That's all I do. Yeah, so what I have actually, I didn't spend much time on this, but one of the things I do is that the reading assignment, so I'll tell them, read the first half of chapter 32. And then on the web, I use a method called just-in-time teaching, which was not developed by me. It was developed at the Air Force Academy and in Indiana at the university by a consortium of a number of institutions, very different from yours and mine. But basically, you give the students 3 questions, 2 of which deal with the subject and are very, very hard. They're not things that you can just look up in the text. You have to think. But the students are told that it's not the correctness of the answer that matters. They have to convince whoever is grading it that they've done the reading and that they've tried to understand the information. And then the 3rd question is always the same. It's, please tell us what you found difficult or confusing in the reading. So before class, those are due the night before class, I press on the button on my website, get the pictures of the students with their names, and they're telling me in 1 or 2 sentences what they found difficult or confusing. You look at 40 and you have a pretty good sense of the difficulties that the students have. So I use their difficulties as questions the next day in class. It's an incentive for them to do the reading because you're telling them basically, if you tell me what you found difficult, I'll help you tomorrow in class trying to resolve it. Well, I don't help you. I'll help you help yourself. In fact, that's, I never get any students accusing me of lecturing from my lecture notes anymore. You know what they complain about now? Professor Mazur is not teaching us anything. We have to learn it all ourselves.
So I also use a technique of asking students to turn to each other to talk in order to solicit answers to questions. But in the past, up until now, I've only felt comfortable doing that once or twice per class period. That otherwise I have to provide more structure. How do you maintain structure if all you're doing is question, discussion, response?
Did everybody hear the question? Should I repeat it? So if I understand it correctly, correct me if I'm wrong, you were using 1 to 2 questions in each lecture period, sort of to presumably wake up the students or keep them engaged. And if I do nothing but questions, how do I maintain structure in the class? And in fact, I do not maintain that much structure in the class. It's very unstructured. The structure comes from the reading and the feedback provided by the students. So if it's a Gauss's law problem and students have difficulties with certain applications of Gauss's law, that's what I focus on. I'll ask a question, and usually I will walk into the class with 2 or 3 times as many questions prepared as I can possibly do. If a question turns out to be too hard, right? I mean, sometimes you ask a question and you find that only 10% of the students get the right answer. It makes no sense to have them talk to one another then, because there are simply not enough students in the audience to explain it to the others. So I'll abort the questions there. I'll explain what the right answer is, or I'll try to nudge them in the right direction. I may, but for example, by telling them that choice number 2, which they all chose, is not the correct choice, that you can rescue sometimes a question that way. And if everybody gets it right, there's also no sense in having them talk to one another. Right? So I decide the structure is by the feedback that I get before class and during the class. So I give them a question they do very well. I give them a harder question on the same subject, or I move on to the next topic. But I take a lot of decisions in class, and I typically, out of my stack of questions, I'll do maybe half at best of what I walk into the class with.
Let's take one more, and I know some people will have to leave. And so in the back. Yeah.
I noticed in your photo you had apparatus for a simple demonstration experiment, which of course many of us find is a powerful learning tool. Now my question is, did you use more of that when you were in the lecture mode, or when you were in the PI mode, or about the same?
Thank you. So the question is about demonstrations, which we actually study. And if you go to my website, you can find a paper on a study of demonstrations. We studied the effectiveness of demonstrations. Now, you said a powerful tool. I also thought a powerful tool. I'm an experimentalist. I love doing demonstration, and if you want to show a phenomenon, nothing is more convincing than seeing it with your own eyes. A study done at the University of Washington a couple of years ago seemed to indicate that students at the end of a semester do not necessarily correctly recall the outcome of demonstrations. So I decided I would actually test that consistently. So we took a large 200-student class and broke it down into 4 groups. And students got rotated among those 4 groups so that there would not be a bias from the level of the students. The 4 groups were: 1, no demo. Those students would see no demo at all. The second group, we asked the instructor just to present, and this was done in a discussion section so that the class would be broken up in groups, because you can't do it in a large lecture hall. The second group, we asked the instructor to do the best possible job explaining the demo, but in a traditional presentation mode. The third group, we had the students predict the outcome of the demonstration before they saw it. So they had a concept test. They had to select between the level of the water goes up, down, stays the same, for example, before it was actually done in front of their eyes. The fourth group, we had them record their prediction on a worksheet, and then they had to observe the demonstration and to check a box that explicitly asked them to state whether or not their observation was in agreement or not with their prediction. So they had to check yes or no. My observation, agrees with my prediction. And then we gave them 2 or 3 minutes to discuss among themselves whether, they had to adjust their prediction or their model of it. So there was discussion. So no demo, present, predict, discuss. And then we did 9 or so demos throughout the years. Actually, we did it 2 years. At the end of the term, we gave them a free response questionnaire asking them to show what they remembered having seen, and then taking that same situation and extrapolating to a new situation to see if they understood the physics and could extrapolate it to a new situation. Now, I'll let you guess. Which of the 4 groups did the worst, you think? No demo, predict. No demo, present, predict, discuss. The present mode did the worst. In fact, there were a couple of students who would write down, as shown in lecture, blah, 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 where the blah, blah, blah is the opposite of what you had tried to show. I was really excited by that. I thought I discovered a new psychological phenomenon. And I went to our psychology department where they laughed at me and they said, you know, we've known this all along. And you should know that too. The way the brain stores information is by making models, not by storing facts. So if you have the wrong model in your head, and you see something that does not correspond to the model, but you are not given the time to adjust that model, right? And that happens when we present a demonstration, we show it, and if you see something that doesn't correspond to what you expect, you would like to think about it, but you have no opportunity because the instructor continues to talk and goes on to something new. So you have to give students time to assimilate the information right then and there and to adjust their model. So the predict and especially the discuss mode does consistently better than the present mode. So yes, I still use it, but I now always have my students predict the outcome and then give them an opportunity to discuss it and try to adjust their model to what they've seen.
Okay, thank you very much, Eric.
Thank you.